Before getting into polar coordinates, we're going to review what angles are, in particular angles in degrees and angles in radians. So angles in degrees, they go from 0 degrees to 360 degrees, and then angles in radians goes from 0 radians to 2 pi radians. So first off, why do we have two systems? Well, the first system is for convenience. So you have 0 degrees to 360 degrees. Right, when you grow angles, you go from 0, you grow in the anti-clockwise direction. So this is positive 45 degrees, positive 90, positive 135, positive 180. This is positive 270, and you circle back and get to positive 360, which is also 0 degrees. The reason this number was shown 360 is because 360 is actually divided by a lot of integers pretty well. So for instance, you can take 360 divided by 2, you're going to get 180 degrees. 360 degrees divided by 3, you're going to get 120 degrees. 360 divided by 4, you're going to get 90 degrees. 360 divided by 5, I'm pretty sure that's 72 degrees. 360 divided by 6, 60 degrees. 7 doesn't work out well, but 8 does, I think 10 does, I think 12 does, all 360 can be divided by a lot of smallish integers and still come out as an integer. So the reason 0 degrees to 360 degrees is common is it's actually a nice way to divide up into a half or a third or a quarter or a fifth or an eighth or a tenth, right? There's a lot of numbers that go into 360. All right, well then why did someone come up with radians? So angles in radians from 0 to 2 pi, and why did they pick those numbers? The reason radians are used is actually for calculus and then, by extension, physics. When you take derivatives of stuff, you want to be taking a derivative of a length. All right, so that implies then that this is somehow a length, and it is. So if I have a unit 1 circle, so it's a circle of radius 1, right? So its center is at the origin 0, 0. It goes through point x is 1, y is 0. X is 0, y is 1. X is negative 1, y is 0. And x is 0, y is negative 1. Circle. It's got a radius 1. And then what's its perimeter? So the perimeter is 2 pi r, but then if r is 1, it's 2 pi times 1. So the perimeter of a unit circle is length 2 pi. And so when you use degrees, it doesn't really correspond to a length of anything, but when you actually use radians, you're actually talking about a length of a unit circle. So to give some context to that, let me draw another one over here. X, y. And let's say I have, all right, approximately, all right, that's 1, and I've got a triangle right there. I drew that somewhat well. What if I draw the unit circle? All right, let's see how well I can draw. All right, that worked out okay-ish. So when you take in degrees, this angle here, I'll call it theta. So theta, that's equal to, it's going to be a 45 degree angle because this length here is 1, this height here is 1, so it's a 45 degree triangle. So it's 45 degrees. If you want to express that in radians though, it's actually the length of this circle, this arc, where you start at the triangle right here and you go up and you wait until there. So it's actually the portion, the length of the perimeter just in that arc is equal to, okay, well, you've gone a quarter of the way. The circle has an entire perimeter of 2 pi. And you've gone, this would be a quarter of the way to 2 pi, to the whole circle. So this would be 1/8 of the entire perimeter of the circle. So it's 1/8 of the entire perimeter, and the perimeter is 2 pi. So you end up with pi over 4. All right, so that's what radians is actually measuring. It's actually measuring a length that you traverse along a unit circle in order to trace out the angle that you care about. Same thing happens if you have a really big triangle. So what if I have 10, 10, yx? So then I've got my dot here. It's still a 45-degree triangle. But now if I draw a unit circle, the unit circle is actually pretty small on there. But if you do trace out this perimeter length again for angle theta, that perimeter length is still going to be, it's 1/8 of a unit circle perimeter. So it's still 1/8 times the entire perimeter length, 2 pi, is pi over 4. And then same thing, you know, this angle here, even though the triangle is bigger, and I think I messed up my dot a little bit, even though the triangle is bigger, we still have a 45-degree angle. All right, so it doesn't matter. What if the triangle is really small? How about that? Okay, let's see if I can... That was a okay-ish circle. What if my triangle is really, really small? What if it's at like a tenth, so I'm at this point? And, or a third, whatever that is. Right, I still have an angle right there, theta. And if I extend out the side of this triangle, I'm still going to be looking for the perimeter length along the unit circle there, which is still pi over 4 perimeter length. Perimeter arc length. And it's still the same number of degrees. This is still 45 degrees. All right? So that's the big difference between these two coordinates, the two ways to describe an angle. An angle in degrees, they picked 0 to 360, 360 in particular, because it's divided evenly by 2, 3, 4, 5, 6, you know, a bunch of numbers. And then angles in radians, 0 to 2 pi, is it's actually the length of the circle you need to trace out the angle you're interested in, the length of the unit circle. All right? And the reason for that, again, is for certain parts of physics and math, you actually need to work with the actual length of something in order for the math to work out correctly, in particular calculus and, by extension, physics. Polar coordinates are a way to describe where a point is in the xy plane still, but it's using, instead of the x coordinate and the y coordinates, it's using an r value and a theta value. And theta is going to be in radians pretty much all the time. So the r value is the distance from the origin that you have to travel to get to that point, and the theta value is the direction to travel, and it ends up being an angle in radians. All right, so as an example, what if I have some point, let's do that one, x comma y. So I want to figure out what the angle is, theta, and I also want to figure out what the length is, r. All right, well, it's not too bad. So if I draw here a right triangle, then I can use trigonometry to figure this out. So the first one, we have the adjacent side length, we have the opposite side length. So the adjacent side length is x. In this case, the opposite side length is y. And I can figure out what the length is of the triangle on the hypotenuse by, you know, c squared equals a squared plus b squared, or c equals square root of a squared plus b squared. So in my case, the hypotenuse length c, I'm representing that by the letter r. And then we have the adjacent and the opposite sides, the a and b, are the x and y values. So it's the square root of x squared plus y squared. And it's the Pythagorean theorem, right? So the distance from the origin to point x comma y is square root of x squared plus y squared, and that's exactly what r represents. For theta, in order to figure out what theta is, we're going to do theta, so I can use tangent of theta is equal to, it's the opposite over the adjacent. The opposite side is y, the adjacent side is x, so its tangent of theta is y over x. And then, if I solve for theta, and there's a little tiny problem with that, but if I solve for theta, it's inverse tangent or arctangent of y over x. The problem here, though, is you have to be careful. You know, which quadrant you're in. X, Y, Z. All right, so let's go and do an example of why you have to be careful with that, just as a reminder. So let's say I've got 4 points, so x comma y, and over here is going to be r comma theta, and I'm going to do 1 comma 1, and let me think here, let me just draw them out. So I want to do these 4 points. So this is x, this is y. I want to do this point, which is going to be 1 comma 1. I want to do this point, which is negative 1 comma 1. I want to do this point, which is negative 1 comma negative 1. And I want to do this point, those approximately in the right place, of 1 comma negative 1. All right. So then from there I've got, all right, let's see here, negative 1 comma 1 for that. And then I've got negative 1 comma negative 1. And then I've got 1 comma negative 1. I want to figure out what those are in terms of r theta coordinates. The first part, it's not that bad, figuring out r. I take this squared plus this squared and I square root it. And because 1 squared and negative 1 squared are both positive 1, all the lengths are going to be the square root of 2, right? The distance from here to here is square root of 2, here to here is square root of 2, here to here is square root of 2, here to here is square root of 2. So that wasn't that bad. Okay. Then for the angles, well, okay, what if we go ahead and use our formula? We can kind of just eyeball the answers. But what if we use our formula? Well, if I take the arctan of, we have y over x here, so in the first one it's 1 over 1. That ends up being pi over 4. So here we get pi over 4. And that looks right, That's angle pi over 4, 45 degrees. All right, well, what about arctan of the rest of them? So let's go ahead and go through here. So I'm going to put y on top and x on the bottom. So then for the next point, it's 1 over negative 1. Yeah. Then for the next one, y on top, x on the bottom. Doesn't matter in this case, it's negative 1 over negative 1. And then arctan on the last one, it's negative 1 over 1. All right, so now from here, let's do this one first, the 1, negative 1. So if I've got, which one is that? 1, negative 1, the last one. Well, okay, arctan of negative 1 ends up putting out negative pi over 4, which is the same thing if I add 2 pi as 7 pi over 4. And I have to be careful, equivalent, I'll say same as, same direction as. Seven pi over 4, right? But they are different numbers. If I calculate negative pi over 4, that's about negative 0.75, something like that. If I calculate this one, I'm not quite sure what that is. But they are different numbers, right? All right, so then what happens in the middle, though? Well, what's going to happen is if you just use your calculator blindly, you're going to end up with pi over 4. And here we're going to end up with negative pi over 4. And this is blindly using calculator. I'll say blindly trusting calculator. The reason those numbers come out is, right, tangent, if you graph it out, I'll say tan of x and x looks like this. So let me give myself a little bit of an aid here. All right. And there. It looks like that. All right, so there's multiple answers whenever you put in, if you put in one x value, there's going to be exactly one value for tangent of x. Right, it's a function, so I'm right here, vertical line test. If I put in x is negative pi over, x is negative pi over 4, I'm going to get this number. If I put in x is negative 7, negative 9, pi over 4, I'm going to get this number. You know, there's vertical line test, it's a function, one line. When you do arctan of x, and I'll say theta, and I'll say x again. That looks like this. Where we've got a vertical asymptote here, and another horizontal asymptote there. And so by convention, arctan is always between pi over 2 and negative pi over 2. All right, so when we plug these in, so let me also write this out. If I have arctan, if I have negative 1 over negative 1, negative 1 divided by negative 1 is the same thing as 1 divided by 1, right? Because I can cancel the negatives. And so this will end up, if you blindly trust your calculator, this thing will pop out pi over 4. All right? Same thing here with this one. 1 divided by negative 1 is the exact same number as negative 1 divided by 1. You're both plugging in negative 1 into here. And so you blindly trusting your calculator, you're going to get negative pi over 4. All right? But that's not right. Okay, so using our college-educated brains here in the process, we are going to have this angle here, this negative 1 comma 1. That is going to be, right, this was 0, pi, pi over 4, pi over 2, 3 pi over 4. I keep going. So this is pi, so that's the same as 4 pi over 4. So this is 5 pi over 4. And I ran out of little room there. Then I keep going. This is 3 pi over 2, which is the same as 6 pi over 4. So this is 7 pi over 4. So you do have to keep that in mind when you're using tangent to make sure you're getting these in the right place. So now, alternatively though, if you are using a calculator or MATLAB or something, there's actually a function that exists to deal with this stuff. So it's usually called atan 2, and you put in usually the value y, comma the value x. We'll add pi if necessary. If necessary to get the right quadrant. All right. The reason this function can be a little smarter is because when you plug in just a fraction, arctan can't tell the difference between 1 over 1 and -1 over -1, right? You're putting an arctan of 1 when you simplify the interior, the input. In this one, it's actually given y and x separately, and internally it's going to do a fraction, but it's also going to keep in track of whether or not y is positive or negative, whether or not x is positive or negative, and then from there it's going to pop out a number blindly from its arctan function. But then it's also going to say, well, wait, if y is positive and x is positive, we better get between 0 and pi over 2, and if it does, then it leaves it. If it doesn't, then it's going to add or subtract a certain number of pi's to get the right angle. And then same thing in the other places. It has a lot more information because it knows where in the quadrants, which quadrant, this point x comma y is, because we gave it those numbers instead of giving them together divided, which we lose some information. All right, so just one thing to keep in mind. If you're using, some calculators might have this now, and keep in mind some of them are x comma y, some of them are y comma x. The more common one seems to be y comma x, but you do need to keep that in mind. I bet you remember that way back when in trigonometry or something. But you got to make sure the angle that you pop out is actually pointing in the white quadrant. All right, so this is how you go from a point x comma y to r and theta, where theta, you got to be careful. And next we're going to do, well, what if we have r and theta, and we want to go backwards to x and y. So going from xy coordinates, also known as Cartesian coordinates, to polar coordinates, we figured out how to do that. You have to be really careful when you do arctangent to get the right theta value. What about the other way? What if we want to go from a point described in polar form, and we want to figure out what its xy values are? That turns out to be not nearly as much of a headache as going from xy for the theta values. We're assuming we're given theta correctly, because that's what we have. We have an r theta point. We want to figure out what x and y are. Well, we can use some trig functions for that. So what if I take cosine of the angle theta? Well, cosine of theta is supposed to be the adjacent, right, over the hypotenuse. And the hypotenuse in this case is the length r. That's what it's defined as. The adjacent side is the horizontal length, and it's the horizontal coordinate in this case. It ends up being the x value. Right, so x comma y. This length here, it's a negative x coordinate, but it's, right, x. And so if we want to figure out what x is, if we know r and theta, we can multiply both sides by r, and we'll end up with x is equal to r cosine of theta. And now here you're given what theta is already, so there's no ambiguity whether or not to add or subtract pi's from it. But you're going to get a positive number r times cosine of theta. Cosine theta is going to pop out whatever it does. Take positive number r times that value that popped out of cosine theta. That's going to be the x-coordinate. All right. Well, what about the y-coordinate? Well, all right, sine of theta. That is the opposite, which is the vertical coordinate, over hypotenuse. So the hypotenuse, again, it's going to be r at length. And the opposite side is the y-coordinate. So it's y over r. Then if we multiply both sides by r, we're going to end up with y equals r sine of theta. All right, so that's not nearly as much of a headache to convert from r theta to xy. Well, okay, what's this good for? So we can use this to translate curves in xy coordinates into r theta, actually. So let's say we've got a half circle here, and this point is 2, and this point is -2. So it's the top half of a circle, and it has radius 2. So the formula for that is y is equal to the square root of the radius squared, so that's 4, minus x squared. And it's, it's the positive square root. If it had been the negative square root, we would have gotten the negative half of the circle down here. So now if we want to convert from x's and y's into r's and thetas, we can just plug in our cosine theta for x and our sine theta for y. So If we do that, we're going to end up with y, okay, so r sine of theta is equal to the square root of 4 minus r squared cosine squared of theta. All right, well, let's go ahead and square both sides. All right, so that's going to end up with, need a little more room here, so r squared sine squared theta, that's going to equal, I've squared the square root, they cancel out, so we get 4 minus r squared cosine squared of theta. All right, I'm going to move the r's to this side, and I'm also going to factor out the r, so we get r squared times sine squared of theta plus cosine squared of theta, parenthesis, equals 4. But now the thing is, sine squared plus cosine squared, well, that's equal to 1. So we end up with r squared equals 4, and then take the square root, we get r is equal to 2. So that's what we've done so far, but we also need to be careful. So really this is a function of r of theta typically. It's just this is such a simple curve in polar coordinates. Polar coordinates are very good for describing circular things around the origin. Is there is no theta on this side, but we do have to keep track of what the theta values are to restrict it so it's not the entire circle. So for this half circle on top, we go from theta is 0 pi up to theta equals pi. So here we have 0 less than or equal to theta, sorry, less than or equal to pi. And then that does make sense. So if I just said, okay, well, I have a radius, a circle of radius 2, and I only have the top half, well, r equals 2 along the entire top half of the circle here, right? All these points, the r value in polar coordinates is going to be 2. And then, right, so I got r of theta equals 2, and then theta is restricted from 0 to pi because we don't have the entire circle. We don't have the pi to 2 pi half. All right, well, what about something that isn't circular-ish? All right, so what if we have a line, let's say x, y again. Let's say I've got this point 3 here. And I have a line, and my function is just y is equal to 3. And I want to convert that into polar coordinates. Well, to do that, I have y equals 3. That's my function. And I'm going to replace all the x's and all the y's with r cosine theta and r sine theta. There are no x's, there's just y. So I have r sine theta equals 3. If I solve for r, I get r is equal to 3 over sine of theta. That's 3, and that's cosecant of theta. And now in this one, we also want to look at, okay, what is the limits on theta? So, okay, it looks for sure that we have theta equals pi over 2, right? That's pointing up. It also looks like we have pi over 4. It's going to look like we have pi over, 8, pi over 16. We're going to have it as long as it's there. If we make a line that is pointing towards the positive quadrant just a little bit, we're always going to intersect this horizontal line at some point if we're pointing up just a little. But it looks like we're not going to have that. So if we have exactly theta is equal to 0, this line y equals 0 will never intersect this line y equals 3. They're both parallel, they're horizontal. So it looks like theta, sorry about that, is in between 0 radians. In the opposite direction, right, if we have pi over 2, that's good. We have 3 pi over 4, we keep increasing. If we get to pi, that's going to be a problem because essentially like you're kind of going to infinity, right? So it's anything a little bit less than pi. So that's going to describe this line, y equals 3. The function r equals 3 cosecant of theta. So let me write that again. R of theta equals 3 cosecant of theta, where we have theta is between 0 and pi. Reason for that is if you graph out cosecant theta, or cosecant x, you end up getting something that looks like this. All right, and then it keeps going. It's horizontal, sorry, vertical asymptote, again and again. All right, so I got to keep that in mind. Well, all right. What about something a little more interesting? What about a circle and we've got this point here, 1. Okay, pretend that's a circle. So its offset, so its center is at x is 1/2, y is 0, and it's over there. All right, well, if we describe this, it's going to be like a circle of radius 1/2. So we have y is equal to square root. So radius 1/2 circle, we're going to get 1/4, so 1/2 squared here. But it's also been offset, so it's offset to x at, positive 1/2, so we're going to also have minus x minus 1/2 squared. Yeah. Okay, so again, we're actually just going to blindly plug in x is equal to r cosine theta, y equals r sine theta. I'm going to get something a little interesting happening. So we've got, I'm going to need as much room as I can, so we've got r sine of theta is equal to square root of 1/4 minus r cosine theta minus 1/2 squared. All right, I'm going to square both sides, so that ends up being, now let's see, what do we got? R squared sine squared equals, oh, squared both sides, the square root's gone. So I've got 1/4 minus, so I'm going to also multiply this out right now. So the first term is r squared cosine theta squared. Then I've got the middle one, so I've got a negative 1/2 times r cosine, and then the FOIL, we get 2 of them, and it's a minus minus, so it's a plus. Let me make it a little simpler here. So minus r cosine theta. And then I've got my minus 1/2 times minus 1/2, so positive 1/4. Right. Then that whole thing is minus, so I have positive 1/4 minus positive 1/4, so those cancel. So I've got negative r squared cosine squared of theta minus r cosine of theta. All right, now if I bring the r cosine squared to this side and I factor out the r squared from both, we get r squared, we get sine squared theta plus cosine squared theta equals, and sorry, I made a little mistake here, right? Minus minus, that should be a plus. It equals positive r cosine theta. There you go. So then this is 1, so we get r squared is equal to r cosine theta. Now we look at this, okay, well, we got to be a little careful. We can divide both sides by r, but we got to make sure we don't get rid of that solution somehow. But if r equals 0, that's actually right here. And then if we describe the whole circle by the time we're done, the whole circle also contains r equals 0, so that should be okay. So we can divide by r, and we get r equals cosine of theta. And that solution, r equals 0, is in there if theta is equal to, what is that, pi over 2? Yeah, pi over 2. then we get 0. If theta is negative pi over 2, we get 0. So the fun thing is, okay, well, what if you were given this? You have to graph it. So let's see. I'll post some examples of that. So there should be like a link up here. It's going to go through actually plotting these things, because that's a little more tricky and it's better to do on a computer.